Here's my free vectors. Here's my free vectors, and that's my third one, numerical one, not parametric one. Numerical one, not a parametric one. So the question is whether this element belongs to a span. It's a very typical question. You will see a lot. It's a very basic example, very basic technique. Doesn't require a lot of thinking. It's a relatively algorithmic approach, like with the linear dependence as well. So again, start off with the definition, with spelling out what it means that the vector belongs to a span. It means that you can find coefficients, lambda 1, lambda 2, lambda 3, such that the linear combination of your x vectors deliver b. Just if you do a parallel with the linear dependence-independence, the difference was here was 0 on this side. There are a lot of parallels between these two concepts, span and the linear dependence. And when you do so, I mean, you solve a system of linear equations. These are the coefficients of first unknown. These are the coefficients of a second unknown. These are the coefficients of the third unknown. So if you skip one step, if you skip the step of spelling out the system, you just can spell out the augmented matrix right away. If you struggle with this, you can do the example one. I mean, you can revisit the example one for linear dependence. There were the same three vectors there, and the system was spelled out in there. And now the question stands whether we can solve this system. Just make a comparison with linear dependence. In linear dependence, the question was how many solutions we have. And the right-hand side was 0. Whereas in this case, the question is, do we have a solution? But again, everything comes down to the row echelon form. That's the row echelon form. And this is the one which will help me to decide whether we have a solution, right? The test is that the right-hand side column in your row echelon form should not be leading column. This column is not leading column because there's a pivot and this is a pivot, and that's it. There's only two pivots in this matrix, and that's two leading columns. Hence, the system is solvable, and the answer to this question is yes. It is in a span. I mean, before it was a question mark. There was a question mark before. We didn't know whether it belongs to a span, but now we do after we found the row echelon form and analyzed that. You can even do the back substitution, and that's what I did here on my slide. You can actually find those lambdas. You need to find b. You can do back substitution. You see, again, in these examples, if you aim to find those lambdas, you don't aim for the parametric solution generally. You don't need that. If your task was simply to solve this system, or this system, or this system, you will need to parameterize. You will need to take the non-leading column, which is lambda free column, and introduce here t parameter, and then solve in terms of that parameter. In this one, we don't have such objective. Our objective is just to find sum. That's why we don't care about the parameter. We choose anything numeric. And unlike linear dependence independence, because in linear dependence we were aiming for non-zero solution. Here we don't aim for that. We aim for any solution. So my first choice is actually 0 rather than 1. And then I solve in terms of this parameter. So if from this line, this is 0, so it will be 3, negative 3. Lambda 2 solution ends up being number 1. Lambda 2 value will be minus 1. And lambda 1 from this row it will be 8 plus 2 of lambda 2's. It's 6. This is a representation. This is a representation for my b vector in terms of x1, x2, and x3. Even though you don't see x3 here, it's still there with its 0 coefficient.